So it's a far interesting one, something you probably never even thought that you could do. You probably even thought you could use trapezoid to do it, but here we are now, right? But what he says is, well, given a curve, let's say, like that. And again, we want to find the area of this curve. What we can do is we're going to be using, let's say, from here to here, this point to that point, we're going to be using parabolas to find the area within this curve. And how we do this is, we just curve here to here, like that, like this, this. So it's a bunch of parabolas going from one end to the other to identify when it comes to it. And all we do is, when it comes to these points, we want to identify, okay, going here to here, up and down, side to side, and all these different type of parabolas, essentially, you want to find the area of these, which is also pretty interesting itself. Okay. So that's the basis of what Simpson's rule is all about, is using parabolas to actually find the areas of these curves. And then notice, right, I did a little bit bad, but, since straight lines aren't completely, symmetrical, it goes through it, curving, right, is the only thing we have parabola shape makes it best to do it itself. Okay? So let's see, is Simon's rule is actually the best of the three types of areas we have. And then using his rule, we have this new equation down here, which again, very similar to the ones above for itself. So you have delta x now divided by 3 is equal to now, again, very similar of the other ones, except now this one is alternates. So the first one is just f of 0. Next one is 4 times f of 1. Next is plus 2 times f of 2, and it rotates in that same pattern. So 4, 2, 4, 2, 4, 2. Again, until the last two do not have the 4 or the 2. And then you always start with 4, and then 2, 4, then 2 as you go along, and that's in the equation itself. Okay. Where again, delta x is the change of b over a over n, and x1 and x are the start of the problem itself. So x1 is right here, x2 or x1, x3, and so forth down the line. Okay. All right, so let's actually try an example to see how in the world you use Simpson's rule itself. Okay. So example 4. So use a rule with n equaling 10 to approximate the integral from 0 to of 1 over x dx. Actually, yeah, I want 1. 1 over x, or 1 to x. Okay. All right, so first off, we want to find change of x. So again, going back, change of x is 2 minus 1 divided by how many we want. In this case, we want 10. So this is going to be 1/10, so 0.1 essentially, right, when it comes to it. All right. So now, according to Simon's rule, it's going to be the change of x divided by 3. So 0.1 over 3 times f of 1 plus, next one is going to be 4 times, and now when we get the next one, we just add it. So 1 plus 0.1 gives you 1.1. That's the next, start at the next parabola, plus 2 times f of 1.2, right? You just keep adding that so forth down the line. And this gives you all the way to f of 2. Okay. And again, right, all you do is plug it in and see what we get out when it comes to it. So like f of 1 gives you just 1. So this is going to be 0.1 over 3 times 1 plus ... all that stuff there. Okay. So again, doing all that information is a lot of work, right, when it comes to it. So for example, I'll give you the next couple so you guys can see the pattern. So 1 over 1.1 times 4 gives you approximately 3.2. 1.636, and keep going. So 1 over 1.1 times 2 this time is 1.667, and keep going, right, when it comes to it. Okay. All right, so then adding it all up and then dividing by this portion here gives you approximately that as its area. Okay. And there we have it. Okay. All right, good. And then lastly, we have the error bound, right? When it comes to assignments, we have error bound for midpoint and trapezoidal. Now, the last thing we have is the error bound for Simon's rule. So, again, very, very similar to what we had earlier when it comes to error bounds. However, this time the equation is a little different. Obviously, the first one, big difference, is now the worst part is we're taking the fourth derivative, which is sometimes, right? After 2 or 3, it takes a little different dive when it comes to it. And also, it's b minus a to the 5th power divided by 180 instead. So, and then this is going to be the 4th as well. So a couple little differences, but notice it's kind of the same pattern. And we're going to do the exact same process as find the k value as we did earlier itself. Okay. So let's try an example out so we can see what's going on here. Okay. All right. So first of all, we got to find the 4th derivative itself. So if it's easier, I'm just going to bring it to this because I know this is x to the 1st power. So we know the first derivative is going to be negative x to the negative 2 power. Second derivative is going to be positive 2x to the negative 3rd power. Third derivative is going to be negative 6 to the negative 4th power. And then finally the 4th derivative. That gives you positive 24x to the negative 5th power. Okay. All right, so again, we know this is bounded between 1 and 2, so we know x is between 1 and 2. Okay. We know our 4th derivative of this absolute value is less than or equal to some k value. Well, let's first write this down first. This is equal to 24 over x to the 5th power. We want this to be less than some value itself, right, when it comes to it. So what we can do the same process. So we know that 1 is less than or equal to x. If we flip it, we get that now. So again, we're going to let 1 over x equal 1, the maximum it could possibly be, and plug it in. Notice we just get 24. So we know for sure whatever x is b must be less than 24. Okay. Well, the absolute value of it, right? Because we're doing the absolute value of it. Right, so therefore, we'll just let k equal 24. So a little easier than the last one, right, when it comes to it. So therefore, the error bound is going to be less than or equal to 24 times 2 minus 1, which is again just 1 to the 5th power, over 180 times 10 squared. Okay. Or approximately 24 over 18,000. And there you go. Right. So that finishes up our section of 7.7.